Hi, welcome to the talk on Physics of Language Models, Part 4.2, Cannon Layers at Scale, while Synthetic Pre-training Resonates in Reality. So this is the third video in a three-part series on the architecture design side of the Physics of Language Models paper series. So if you have watched my first two videos, welcome back, glad that you're still with me. If not, that's totally fine. This video is going to be fully self-contained. To recap, most architecture research today is still conducted at what I call academic scale, that is up to 1.3 billions of the size of the model, pre-trained for 100 billion tokens. So in the first video, I showed that at this academic scale, then real-life pre-training can be extremely noisy. So you might find one architecture that looks better than Transformer, but with a different random seed or slightly better tuned hyperparameter, the conclusion can easily flip. So I have given you like some very strong counterexamples in the first talk. But then what can we do with it, right? How can we perform trustable architecture design research? So in the first two videos, I was advocating for this idea of building a versatile synthetic pre-trained playground for the purpose of quantifying an architecture's capability across each of the skill dimensions like more cleanly, for instance, the reasoning dimension and the knowledge dimension and so on. The way to do that is to say that suppose I focus just on one of the skills, like the knowledge dimension. Then I can create some synthetic knowledge dataset, and then I only pre-train my architecture on top of this specific dataset to see like how good this architecture is in terms of, say, storing knowledge. And you can do the similar thing for different kinds of reasoning and so on. So the one of the good consequences about that, especially if you design the playground like very carefully, is that now like you no longer need to pre-train a large model. It suffices for you to train a model that's only up to maybe 100 million parameters. That's GPT-2 small scale, and that turns out to be more than enough for you to derive some very interesting architecture principles. So this is what we did in the second video. And one such principle and one such architecture component we discovered is the so-called cannon layers that we introduced. I'm also going to briefly recap that today. But towards the end of the second video, I also told you that some of the principles we discovered using the synthetic playground are totally not observable if you use an academic scale real-life pre-training. So this raises a natural follow-up question, that is, are those results therefore still meaningful? So this motivates basically today's talk, today's video, part 4.2. That is, we now show that the cannon layers we discovered over there actually perform extremely well at scale. So this time is like 8 billion of the size of the model pre-trained for 1 trillion tokens. But this talk is actually more than that. So more importantly, we ask deeper questions about where do insights from the synthetic pre-train actually show up in those real-world training. So this talk, therefore, is not just about scaling up. It's also about learning new lessons from the real-world pre-training. And at such a scale, we can even discover some new linear architecture improvements over the existing ones, like GLA and GDN, like the linear attention or gated delta net. And also very crucially, we're going to conduct a very strong and controlled and vertical comparison across architectures, between transformers versus several different versions of the linear models. And this is going to be backed by 2 million of GPU hours of training. So my hope is that those results will offer not just only bigger numbers, but more importantly, a clearer picture, a clearer lesson about architecture design at scale. So let us begin. To recap, as I said in the first video, I showed that at academic scale pre-training, architecture differences are drawn in noise. So this was the table I showed you, that is, you can pre-train a transformer or the llama architecture, but with varying random seeds. Maybe random seeds for both the data and model, or maybe you can fix the data, but only vary the model's random initialization seeds. But you see that in both cases, the result can have a very large variation in many of those standard benchmarks. But in contrast, if you look at some state-of-the-art linear models, for instance, and look at their claimed gains on top of the transformer architecture, so those are actually much smaller than those variations. So therefore, like I summarized using this little box inside the first video, that is, across random seeds, maybe 8 random seeds we tested, the variations of those benchmark accuracies can sometimes be much larger, and in most cases actually much larger than those architecture differences. So therefore, like, how do you conduct like trustable architecture design research? So in the first 2 videos, I was talking about using the idea of the synthetic pre-trained playground, but today it will be totally different. Today it will be the opposite, that is to scale things up. But easier said than done, like when you actually try to scale things up, there are at least 4 different dimensions you have to get right. The first dimension is to choose the best kind of pre-trained data. So in the old days, people used like Sling Pajama for pre-training, but nowadays, like the quality, especially like the internet data's filtering has been like greatly improved. So therefore, the quality of the pre-trained data has become like better and better. So this naturally reduces the training time. You know, if you want the model to achieve the same kind of performance, now like it requires a fewer number of training steps. But another dimension of things you can do is this idea of paraphrasing or rewriting. So this was nicely done by NVIDIA's Nemotron CC data, or Nemotron CC2, which was recently released. So those data sets actually followed a guideline that we proposed about 3 years ago in our part 3.1 that we call knowledge augmentation. So over there, we discovered that in almost all the cases, instead of like using the same pre-trained data like multiple times, like especially like the Wikipedia data, for instance, the third time you pre-train it, you actually had better paraphrase it or rewrite it using, for instance, one of the following 3 prompts. Like you can try to rewrite the above text and using like a third-party model, or you can ask that model to translate the pre-trained data, or maybe to extract some Q&As from the data. So if you do this kind of paraphrasing and rewrites, and then you use this newly built thing as your new pre-trained data, then this can actually improve the model's performance a lot. So we explained what's behind the scene, like what's the theory behind it in that paper. But today, let me just summarize everything like using this simple 2 lines. That is, with rewrite, actually knowledge can be stored in a better format in the model so that the knowledge can be more flexibly used for downstream tasks. But if you don't do rewrite, then even if the same piece of knowledge is exposed, say, 100 times in the pre-training, then the model may just be memorizing the knowledge, but the knowledge cannot, memorizing the knowledge, say, word by word, but the knowledge cannot be actually used for downstream tasks. So in reality, as a consequence, if you don't do rewrite, then you have to wait until each piece of the knowledge to appear in sufficiently many natural rewrites online, because people are going to talk about the same knowledge, maybe on different internet forums, in multiple different natural rewrites. So therefore, like you don't need to actually rewrite. You can wait until like you see like more training tokens, but this approach is definitely like much slower, right? So you want to manually like inject this kind of paraphrased or rewrite format of the pre-trained data in order to reduce your training time. So this is actually an orthogonal technique comparing to the data filtering, and you need to do both in order to get kind of the best quality of the pre-trained data. So therefore, like in today's talk, I'm going to like pre-train models only using the Nemotron CC data. A final comment here that is, so here like you see that I'm using some maybe third-party LLMs to do this kind of paraphrasing or rewrite. But this is totally different from those LLM like hallucinated synthetic data, like the Phi series of the data. So over there, like you may have issues of data contamination, but here, like I'm just doing some paraphrasing. I'm not injecting, I'm not producing like hallucinated knowledge. I'm just paraphrasing. So you have to do this in order to get the highest quality of the pre-trained data. The second dimension you want to do is definitely to train longer, but not insanely longer. So here is the setup that we decide to take. That is to pre-train for like 1 trillion tokens, or sometimes 2 trillion. And then these are the model sizes we take, like 1 or 3 or 8 billion of the size. And this corresponds to this number of GPU hours of pre-training if you use H200 GPUs. And there are therefore like as a minimum of like 10K or 20K or 50K of US dollars of pre-training. So I was very fortunate. I was supported by FAIR at Meta to conduct this scale of the experiments. But more importantly here, I want to emphasize that you don't just want to run it once. You want to actually repeat such experiment across between 2 to 3 like best learning rates. So here, like I'm emphasizing on two things. One is the word of best. Okay, so if anything I learned from the field of architecture design is the following: that is, do not trust other people's hyperparameters. So let me show you like this paper from the field of optimizations that I'm going to actually keep citing a few times today. So they discovered, for instance, quote unquote, like the speed up of many proposed optimizers over well-tuned baselines can be much lower than claimed, if you just, tune the parameters more accurately. And things are similar here, like for architectural research, right? You really have to, tune the parameters correctly in order to perform the correct kind of architecture comparisons. So I'm going to also show you like some very strong examples about, if you don't do this right, then what bad things will happen. And a second thing I'm emphasizing here is this word like between 2 and 3 learning rates. So if you run the experiment, multiple times and take, for instance, the max of the performance or the mean or the median, they can definitely suppress noise. So some people do this by repeating the same learning rate, but across 2 different random seeds and so on. But I prefer to do it differently. That is, I prefer to test the same kind of model, or the same model, but across like 2 kind of close enough learning rates. So this way that I'm both kind of testing the model's robustness against this kind of randomness, but also I'm testing if my learning rate is actually correct, because for some of the benchmarks, maybe a slightly smaller learning rate will give you like a higher score, but sometimes like a larger learning rate will give you a higher score, and so on. So therefore, like I propose to really do between 2 and 3 best learning rates in order to suppress the noise before you do the architecture comparison. So the third dimension, actually the most interesting thing of today's talk, is that we have to actually tighten the experimental controls before like you compile the architectures. So this means not only like when comparing architectures, you want to make sure the training data are the same, the randomness, the shuffling are the same, the tokenizer are the same. You also want to make sure like the model's depth are the same, the hidden size are the same, and also maybe the training code pipelines are the same. But even on top of that, when studying like model architectures, you had better make sure the models are also maximally aligned. So if you're talking about transformers, this is easy, because when talking about, say, 1.3 billion of the transformers, people already have like a fixed kind of configuration. That is 24 layers of the model, and the hidden dimension being 2048. And they typically use this like 4D square plus 8D square configuration, namely like for each transformer block, you spend 4D squares of trainable parameters on the attention side and 8D squared parameters on the gated MLP side. So this is what people typically refer to as the 1.3 billion of the transformer. But when talking about linear models, things are much, much more involved. So for instance, when talking about Mamba, people typically mean, at least the original authors, they mean the version of the Mamba without MLP. So they do, if it's like 1.3 billion of the size of the model, they mean like 48 layers and 60 squared plus 0. But when people talk about like gated linear attention or maybe gated delta net, their default configurations are also different, like 4D square plus 80 square and 60 square plus 60 square. So therefore, like if you just naively like compile linear architectures by taking their default configurations, already here you see like a large discrepancy, right? If one architecture is better than the other one, is it actually because of this, split between the MLP and the linear model side, right? Is it because, for instance, Mamba doesn't have MLP, so it performs bad? So you have to already, tighten, many things here about this kind of sub-configuration. But much more than that. So when talking about linear models, you have to also pay attention to recurrent memory size. So for those of you who work in this field, you may recognize what I'm talking about. That is, Mamba in its default configuration may actually use twice the size of the recurrent memory comparing to GLA, or 3 times the size of the recurrent memory comparing to GDN. So therefore, like when comparing architectures in a very fair manner, you have to also tighten like the recurrent memory size to make sure when talking about linear models, they spend the same size of the recurrent memory in terms of how much piece of information they can store about the context in the past. But even more than that, right? You also may have to tighten the number of attention heads, or maybe the head dimensions and so on. So this actually requires some very non-trivial research, which I'm going to show you today. And overall, like, I just want to say that, when aligning those models, you have to at least make sure like you have equalized recurrent memory for linear models, as well as like some fair design on the number of heads and the head dimension and so on. So only after doing this, okay, you can remove a lot of the hidden factors that would otherwise totally distort the comparison. So this is actually one of the main focus of today's talk. And by the way, like, because we spent so much time in this direction about tightening the experimental controls, actually as some byproduct, we discovered some linear architecture design improvements that I'm also going to show you. So the fourth dimension is this dimension of post-training or RL. So during the post-training stage, people can inject a lot of like high-quality reasoning data here. So therefore, like the model's performance will be just much higher during after this stage. But I want to claim that, if you want to focus on architecture design, then maybe you don't want to, use this type of data, because, if you put post-training, also bring post-training in to study architecture design, then it becomes much harder to tell like what may have actually caused the improvement. So if, like, for instance, like in the end of your code pipeline, like you see some very good performing like architecture, but does this improvement actually attribute to the pre-training, or does it attribute to the RL optimizer, or does it attribute to the RL objective, like the GRPO, like the PPO, those kind of POs, or does it actually attribute to your architecture design in particular? So therefore, like, if you like do post-training on top of this, of course, in practice, you want to do that. But if you want to focus on architecture design research, this could give you much more noise and make the result even less trustable. Therefore, like for today's talk, I want to defer this, and I want to mostly just focus on pure pre-training. But I promise at the end of the talk, I'm going to revisit back to this point in result 7 over there. Like, I'm going to connect our results actually to the post-training as well. But most of the talk will be just focusing on like pure pre-training using the Nemotron CC dataset. So let us begin. The first result is regarding transformer plus cannon layers. Let me recap a little bit what is the cannon layers from the first video. So how does a transformer work? So transformer, takes token, and it forwards each token in its like depth dimension. And inside the transformer, whenever you want to say have two tokens to communicate, you have to rely on this very non-trivial attention mechanism, which is very heavy. But very often, as we discovered in the previous video, you may just want to know what is your previous token, or what is like your previous two tokens. So therefore, like, I advocated for this idea of adding more horizontal information flow to directly support this kind of operation without invoking attention. Okay, so this is what I call the cannon layers. So in particular, there are many ways to implement cannon layers. A particular one we used was as follows. That is, for each like hidden state, maybe HT at time horizon t, say it's of dimension m, then you read what are the previous 3 hidden states, and then perform just a one-dimensional convolutional layer with trainable weights. Like, those are coordinate-wise multiplications with trainable weights and one conv1d layer, and let the result be called, say, HT prime. And now, like in the past, you just forward your HT to the next layer, but now you use your HT prime to forward to the next layer. So this is what I call cannon layers. And a particular implementation we were advocating is this residual format of the cannon layers. Okay, so therefore it's H plus this conv1d. Some people call it causal conv1d because it only reads to the left. So we explained in the previous video that there are many different ways to implement this, and in the end of the day, actually the specific implementation may not matter the most. What matters the most is actually where you add it. So especially for a transformer, each transformer block can be decomposed into 2 attention layers and 2 MLP layers. And this gives rise to 4 natural points for you to insert such a horizontal information flow. So therefore, what we advocated in the previous video is to insert full score canon, what we call it. That is to insert canon ABCD. So insert this kind of operation at all of those points as much as possible. So in the syntactic playground, we discovered that this is extremely helpful. And that's actually just the end of the recap of the previous video. So now, you already maybe know that what canon layers are and how does it work on top of transformer. And in today's talk, let us see that how much it performs if we scale things up. So we conducted actually 16 controlled runs, and here is how they look like. So we're going to experiment with 8 billion size of the model pre-trained for 1 trillion tokens, and 3B for 1 trillion, and 1.3 billion for 1 trillion or 2 trillion tokens. So you see 8 rows. Each row is actually a max over 2 learning rates. You can also take the mean, it's similar, but here I'm taking the max. But the important thing here is that if you look at all those even rows, so those are the rows corresponding to adding canon layers, but all the rows correspond to the ones without canon layers. And you can already see that in this table, which is the standard LM evolve evaluation benchmark, then you see this is the average score, this is the individual scores. You see that adding canon layer already gives you a clear gain over the case without canon layers. So this, by the way, very importantly, cannot be observed if you do an academic scale pre-training. So in the second video, I showed you that if you do 1.3 billion of the model pre-trained for 100 billion tokens, then those are the transformer performances. But I tried 3 different variants of the canon layers, but none of them actually see any significant gain comparing to the thing above. So therefore, if you scale things up, those gains actually do show up. And by the way, also to emphasize that this is a very strong comparison because I'm making sure that the data, the random seeds, the tokenizers are all aligned. So therefore, if something is better than the previous row, it's actually a very strong kind of comparison. So we have released the entire code pipeline, and also the model weights are also fully released. By the way, the gains not only stand here on those LM evolve benchmarks, they also extend across a diverse set of skills. So we also tested many other benchmarks, including retrieval or generative tasks, and we see that the canon layers are much better than the without canon layers. We also tried to test the model's performance on length generalization, and the canon layers are better than without canon layers. And we also tested the long context reasoning, the so-called Babylon dataset, and it's also a lot better than the alt layers. So that was a brief snapshot of those accuracy numbers that, showing you, maybe convincing you that canon layers are better. So you're very welcome to check the full table that we have released in our repo. But for the rest of the talk, I want to actually focus on everything beyond this table. Okay. So the first question we should ask, whenever seeing a table like this, is that are we actually studying an interesting regime, or is this a toy setting? Okay, so I want to tell you that no, we're not studying a toy setting, and here is the way I see it. Okay, I'm going to compare our 16 trained models to many of those open sourced models. Okay, in this table. So let me explain. In this table, the x horizon is the model size times the number of training tokens. So therefore, 1 BT is roughly equivalent to about 5,000 of H200 GPU hours of pre-training. So therefore, the X horizon captures how long it trains, and the Y horizon captures the average score over 10 of those standard benchmarks. So just from the something like the table above. So the first observation I want to make here is regarding those raspberry pink points. Okay, so those raspberry pink ones correspond to 8 billion size models. So we are here. Okay, so we have 4 dots. So the 2 solid circles correspond to Llama, the transformer, plus canon layers, and the open circles correspond to the original Llama architecture. But let's compare it actually to this triangle here. So very interestingly, this was released from the Nemotron CC paper. So they pre-trained on the same dataset, the Nemotron CC dataset, for the same size of the model, 8 billion size, for the same number of tokens, 1 trillion tokens. So therefore, it's exactly in the same setting as we do. but maybe slightly different architecture configurations. But what we discover is that they're not using the best hyperparameters. So we are also using llama. So those two open circles correspond to llama, right? So we are also using like 8 billion size of the model, but we can be a lot better than theirs. So this is one of the importance about really tuning the best kind of hyperparameters. And I think in order to study architecture design research, you have to at least be very careful here. So I hope this is actually a good signal that we are at least using a very much better choice of the hyperparameters, at least comparing to the original Nematron CC paper. And another thing to point out is actually those three results correspond to also that same Nematron CC paper. So they discovered that if you use the Nematron data versus the DEC-LLM data versus the FireWeb EDO data, then you see this accuracy boost, right? So this highlights the importance that I said earlier, that is, you had better use a very good high quality data. So another thing I want to point out is this horizontal comparison. So we are only here because we are only pre-training for 1 trillion tokens, but most people pre-train for a lot more number of tokens. So for instance, here we showed some models pre-trained for between 4 and 15 trillion tokens. So what we find out quite amazingly is that our performance are kind of on par with those models, especially if you look at Llama 3, 8 billion, we have even completely beaten it, despite only 1/16 of the pre-trained time, right? So I'm not actually bragging here. So of course, we are only competitive to Quant 2, but not to Quant 3. Quant 3 is maybe here. But the point is that those models that we are pre-training here are really not a toy setting. Okay, so those models can already perform very strong tasks and are really on par with many of those models sitting here. So not only for our 8 billion trained models, also for our the black dots correspond to 3 billion trained models, and the green dots are the 1.3 billion size models. So those are actually our models. Okay, so they are very strong competing to those other models pre-trained even for longer and so on. And it is the fact that in all of those cases, we discovered that the Cannon layer consistently gain that made us to confidently claim that the Cannon layers really work in practice, really work in large scale. Okay, so this is this is result one. That is, we showed that in this setting that is truly not a toy setting. In real life, that if you pre-train the transformer and using Cannon layers, and this is how much gain you can get. Now let's come to the second result. So in the second result, I want to advocate this idea of not just reading a performance table, but let's this time read a benchmark curve. Okay. So for instance, if you look at the MMLU benchmark accuracy, you can plot it as a curve in terms of the number of training tokens. So we have 16 models here, right? So 8 billion models and 3 billion models. The solid ones are with Cannon layers, and the dashed ones are without the Cannon layers. And for the 1 billion model, we also trained for 2 trillion tokens and so on. So now, if you look at this benchmark curve, I claim that it becomes much clearer about which architecture is a better one. So you see, for instance, without Cannon layers, transformer is here, but with Cannon layers, you really get this much of the gain. So one thing that's really critical about reading a curve like this in comparing to a table here is because of those bumps, right? So for instance, if I'm not lucky and I early stopped my training, for instance, here, you can see that this is already a 2 or 3% of difference in terms of the MMLU accuracy. But if I stop correctly at the end, then I no longer have this bump and so on. So therefore, all of those benchmarks can be actually very bumpy. So if you only look at their final numbers, that could sometimes be misleading. So it's actually better off if you read such a benchmark curve. So this is not only just true for MMLU, but it's also true for every other kind of reasoning or those real life benchmarks. So some of them are actually much better. For instance, the HellaSwag data, because of the size of the data, it's actually very stable, so that you can see which model is better, more cleanly. But some other benchmarks, the Arc Challenge, are much noisy. So for instance, here you can't even see which one is better. So in such a case, you may have to do like a moving average. For instance, if you do MA5, a moving average of 5 points, this time, this architecture gain becomes more visible. So therefore, like I want to really advocate for this idea of, let's maybe not focus on the performance tables, but let's look at the performance curves in order to truly figure out, how good an architecture is. And on such a table, you can also read off some, quantitative performance gains. But by the way, like we have released not only all the 60 models, we also released all the full like interactive charts. You can play with it to see like the all those performance charts with respect to all different benchmarks. But I want to say that using these curves, you can also see very cleanly about how much is one architecture better than the other one. So for instance, here I can confidently say that Cannon can save about 30% of the pre-trained tokens for the same accuracy target. So, and this 30% gain remains very strong, even at this like 80 billion of scale. So how to read it, right? So if you want to achieve this accuracy target, then all you need to do with the Cannon layers is to stop here. That is, you only need about 70% of the pre-trained tokens. So this is how much you can save. So I want to like really emphasize how important, like how significant this is by comparing it to the following paper. So in this same paper that I already cited, they said modern optimizers speed up. So for instance, the Muon optimizer really reduced to about 10% when scaled up to 1.2 billion of the size pre-trained for 200 billion tokens. But if you think about it, we are actually 30 times more than their scale. But our gain remains really solid, even at this scale. Okay, so I hope this is, they were studying optimizers for sure, but we're studying like model architectures. So I hope this is a clear evidence that, we are not only studying a setting that is not a toy setting, but also a significant gain that really holds strongly even at a large scale. So this actually summarizes just result 1 and 2. So they together just say, yes, Cannon layers still work at scale. So this part is reassuring and thankfully like not very surprising. But now comes kind of result 3. So this is where like things start to get more interesting. So here I'm going to introduce you a unified and fair framework for comparing transformers and the linear architectures like all together. Okay, so the general, to start with, we want to align all the model families under the same design and training budget. So this means that, as I mentioned earlier, that whenever you want to compile two architectures, you want to align them to the same depth, the same hidden size, the same data, random seeds, and shuffling and training pipelines, and to pick like 2 or 3 best learning rates. So this sounds easy, but in practice, trust me that this kind of alignment really removes more breakthroughs than it creates. Okay, you'll be surprised at how many so-called breakthroughs really disappear once like things are properly aligned. So in the end, after such alignment, we are going to train like 48 linear models plus like 16 transformer models that I already did in the previous 2 results, and that totaled actually 1.3 million of GPU hours. So this actually doesn't even count our research GPU hours. We spent another 1 million research GPU hours just for the purpose of alignment, which you are going to see. So among the linear models, we tested actually 3 of them. Gated linear attention, or GLA, is arguably the simplest form of linear models. It's just linear attention, but with gating. And the Mamba2 and the GDN, or gated delta net, so they underpin today's largest open source hybrid LLMs. So we are also going to test them. So we are going to test not only their original versions, but also the versions with our Cannon layers to see how Cannon layers perform. But now comes the interesting thing. That is when, as I mentioned, when comparing linear architectures, we really need to spend some extra care to align them properly. For instance, when talking about the GLA, or gated linear attention, versus GDN, or gated delta net, you already see that those 2 architectures have some discrepancies. For instance, when talking about the GLA, it's typically like 8D square of trainable parameters on the gated MLP side and 4D square on the GLA side. But it's like 6D square plus 6D square on the GDN. So therefore, like the first step about this alignment is that you want to make sure it's 6D square plus 6D square. But the second step, that is actually something we discovered, and very, very interestingly, is this output gate. Okay, so what is an output gate? So in both GLA and GDN, they have this output gate. So they perform the following. That is, previously you have an output that's maybe this GDN or this GLA function, and you compute the output, but you don't directly use the output. You multiply on top of this output the following like gating mechanism. That is, so let the hidden state be H, then you apply a linear layer, then some like normalization, and then say a slew activation, and then use this as a gate to multiply on top of the output, and use that result instead of your original output. So we propose actually to do something totally different. That is, we propose to do a low rank version of the gating. That is like represented by this G1 times G2 with, for instance, an inner rank of only 16. So the overall goal is to actually save the parameters and use the and put the parameters actually all into this like GLA or GDN side, so that you don't waste the parameters on the gating. So why is this so important? Let me explain, and let me actually use an analogy. So in the traditional case, when doing gated MLP, which is actually this part, you also have this kind of gating. That is, on one side of the computation, you have a linear like layer, but on the other side of the computation, you have a gating. So you have those like two linear things, and then one side you have nonlinearity and multiply together. So that was the so-called gated MLP. So in gated MLP, you don't want to have low rank. You will want to have full rank on both sides, because gated MLP is so simple that both sides are just linear operations, so that in the end, your like optimizer, your SGD or Atom, can actually very perfectly align kind of and couple those features on the two sides together to give you some very very strong learning of the nonlinear features. So I'm skipping a lot of like the theory details here, but the point is that if both sides are simple, then this gating actually starts to play a very strong role. But in our case, it's very different. Like the GLA side and the GDN side are very complex. Those are complicated functions. So therefore, the gating, you can still do it, but its functionality is going to be much weakened. Okay, so that's just because like you're just optimizing over like a very complex function, and if you hope that your gating side could kind of couple with the GDN side, then maybe there exists ways to perform such coupling, but your optimizer may not find, a very strong like coupling. You may in the end just learn some gating as simple as just maybe canceling some of the directions, or maybe just overall like scaling down this layer by a small factor or something. So therefore, we propose that because you're not learning some strong like gating, then why not just make it simple to begin with? So this is our proposal of this low rank version of the gating. So if you have watched my previous video, you may recognize this picture I was advocating. That is, I think in the field of deep learning and AI and LLM, like in general, existence is cheap. You can design like an architecture that's very complicated, like this gating mechanism, for instance. But it doesn't mean that the optimizer is going to learn it. So in the end, it may just learn some very simple function, and therefore, like in the end of the day, why not make your architecture just simple to begin with? So this is actually behind our design. So if you use a low rank version of the gating, then we also propose to use a low rank version of the initialization. So if originally you use some STD for your like initialization of the gating side, that is, this matrix G may have each of the entries having a standard deviation of STD, then in the new design, actually you'd better use STD that's equal to the square root of that times the rank to the negative to the 1/4. So this is for the purpose of ensuring that at random initialization, if you use this like low rank if you use this low rank design, then it's like vector norm is roughly the same as the original full matrix. So it makes sure like, if you transfer from this original full gating to this low rank gating, you're not losing much. So that was actually how we discovered this kind of performance gain, by performing this kind of very controlled comparison. So this is our low rank initialization. So in the end of the day, we just discovered this kind of improvement, and we call it like GLA 5 on top of GLA, and we call it GDN2 on top of GDN. So those are some code names. Don't ask me like why I call it GLA5, because I have some GLA2 to GLA4 that maybe I will publish another day. So in fact, we discovered all of this, not as a coincidence. We discovered all of this like using our synthetic playground from the previous two videos. I could maybe have already written a totally new paper just for this part, but the important thing is that they work. So I'm not showing you all the kind of analysis using the synthetic playground. I just want to tell you that they truly work, and I then tested it on this like real life scaling, and it performs very well. So the more important thing to today's talk is that after this improvement, now suddenly the two architectures become super aligned. So if you think about it, their only difference now is on this GLA and the GDN side. So everything else about the dimension, the number, the query dimension, the key dimension, the value dimensions, everything else like really match. So this provides a very strong like alignment, so that in the end, if you truly, if after this alignment, you still see like one architecture is better than the other one, now you can confidently claim that it's the GLA or maybe it's the GDN gadget that is playing a role. So this is how we align the GLA and the GDN. And by the way, like you had better also align the Mamba architecture with this, but Mamba is slightly different in terms of the architecture design. So what we did is to at least ensure that its MLP and SSM split remains to be 6D square plus 6D square, and we did not change any of the Mamba 2's architecture on its own. We only changed the GLA and GDN. So to recap, among those linear models, I redesigned GLA into GLA5 and GDN to GDN2 to improve performance. And more importantly, I made sure the linear models are super aligned. So I made sure like their MLP sizes were equal and the query key value dimensions equal. And also something I didn't cover, but it's actually, if you know this field of architecture design, you know what I'm talking about. That is the recurrent memory size can also be tightened. So that you can make sure that no architecture gets extra memory. So linear models are just like RNNs, right? They spend a specific number of parameters just for the purpose of storing like what is there in the entire context so far. So therefore, like that, the size of that recurrent memory actually matters. You want to make sure like all of the architectures use the same kind of memory size. So we also tighten that. So in the end of the day, this is actually a quick kind of summary of our architectures, comparing like Llama, like GDN or GLA5 or Mamba 2. So as I said at the very beginning, we made sure that the model size, the depth, the hidden dimensions, the tokenizers really match. We made sure that the random seeds, the random shuffling, the total number of training tokens all match. And we also open source the code that works for all of the models. And also, like I told you on the previous slide, that we made sure the linear models are like also super aligned, so that they use the same number of heads, the same recurrent memory size, and also the same like 6D square plus 6D square configuration. But something else that's here, that is for linear models, actually, we are going to use a slightly longer context length. That's because for linear models, it's actually always better to use a longer context length, because you no longer have that quadratic kind of time dependency on the context length. So therefore, as long as your GPU fits, for instance, if you want to compile like a case of training for context length of 4,000 with 512 number of batch size, but if your GPU fits, then it would be better if you pre-train like for 16,000 context length, but with only 128 batch size. So therefore, like we are training the linear models with sometimes a larger context length, because why not? It's always better. And the last comment I want to make here is for optimization experts. You may recognize what I'm talking about. That is, here among the linear models, I'm going to give it a little more advantage. So for the linear models, sometimes I tune like over, I'm going to present the result to show you the best among 3 learning rates comparing to the 2 learning rates of the transformer models. So the reason will become clear towards the end in result 6, because I want to like make some strong comparison between the transformer and the linear architectures. So therefore, I want to give a little more advantage on the linear models. And also the linear models are trained with slightly more number of steps, although the number of tokens are the same. So each step is like half in the size, but a little more number of steps. So this also gives linear models a little more advantage. Okay. So similarly, for like 3 billion and 8 billion models, we tighten everything and make sure the linear models are, aligned among themselves, and also like having a little more advantage comparing to the transformer models. So that is result 3. So I provide you some, strong and super aligned linear models, and for the purpose of getting some strong comparisons. So in the next result, in this result, let us see that how linear models perform on top of Cannon. Okay. So I've shown you this picture for transformers, but for linear models, actually, it's also of a similar configuration. That is, each block consists of 4 sublayers, and now the first 2 sublayers will correspond to maybe the linear attention, or maybe gated delta net, or maybe the Mamba SSM architecture. So therefore, like, on top of a linear model, you can also talk about adding Cannon layers, that is, adding this horizontal information flow. So what makes linear models a bit different from transformers is that linear architectures authors have already introduced some horizontal information flow. So they have already introduced a conv1d layer at point B. Okay, so we call it Cannon little b because it's actually a bit different from our design of the Cannon layers. So if you allow me to think, so I believe the original authors of all of those linear architectures, linear models, they actually noticed that linear attention is weak. So therefore, like, let's support some, let's add the conv1d to make it more like a multi-token kind of linear attention. So they see some performance gain. So that was maybe the rationale behind like why they add a conv1d inside at this point B. But what we discovered in the previous talk is that if you remove this conv1d, then all of those linear architectures' performance can be really, really bad. So it doesn't matter if it's synthetic or real-life performance. So therefore, like, we made a very strong conclusion over there that is most of those linear models' performance actually comes from this conv1d layer, but not maybe from their architecture smartness. So if you think about it, because of this importance of this, conv1d layer at point B, then it makes actually a lot of sense to actually increase the number of such horizontal information mix. So that was what we proposed in the previous video. That is to add Cannon layers as much as possible. So therefore, like, what we call full score Cannon in on those like linear models are exactly this so-called Cannon a little b CD design. That is on top of like their already proposed the Cannon B, we add additional like Cannon ACD in our own version of the Cannon layers. And then we're going to raise the bar today. That is, we're going to compare like Cannon A little b CD to their Cannon B design and see how much the gain there is. Okay, so this is like Cannon layers on top of linear models. Now, the biggest discovery here is that linear attention, if you do Cannon layers, it performs extremely well on top of the original gated linear attention. So here we are comparing GLA5 versus GLA5 plus Cannon. So we see that on this MMLU benchmark, then you see like the solid lines correspond to GLA5 actually versus the dotted lines, which correspond to the GLA5, but without the Cannon layers, you see about a 20% of the pre-trained token saving on this data set, even at this 8 billion / 1 trillion token scale. So if you look at 3 billion or 1 billion, like the gain is even much larger. So keep in mind that this is actually the best curve out of 2 to 3 learning rates. So therefore, we have already done this procedure of taking the best among the learning rates in order to reduce noise. And also here, like, we are actually a little conservative because we're comparing the ABCD versus Cannon B. So this comparison is actually on top of GLA's already built-in conv1d mixing. Okay, so if you compare it to the version without the conv1d, then the gain would be much, much larger. Okay, but we're actually raising the bar. So it's not only true at MMLU, you can look at other benchmarks like the Common Sense QA. And here, like, maybe you don't see that much gain on the 8 billion size, but you see much gain, a large gain on 3 billion and 1 billion. if you look at Arc Challenge, you no longer see a large gain on 3 billion, but you see a huge gain on the 8 billion and so on. So therefore, like in all the cases, you see like that adding Cannon layers never hurt, but they only like improve the performance, and usually by a lot. So similar gains can also hold on the original GLA design, but our like improvement, GLA 5, performs generally better. So therefore, like for this entire talk, I'm only going to focus on GLA 5 instead of GLA. So this is the performance chart. This is the benchmark curve. But what about the benchmark table? So if you look at the LM Evolve like benchmark table, you're going to see it also performs very strongly. So here, like our 3 blocks, the 8 billion model, 3 billion, and 1 billion, and each block has 8 rows. They correspond to Llama, Mamba 2, GLA 5, and GDN2, and with or without Cannon. So let me highlight like this row in each of the blocks. So these are exactly the GLA 5 plus Cannon, and you can see that it's actually the brightest, in each of those categories. So therefore, like I can say that, GLA 5 plus Cannon is really like performing on par with GDN2 plus Cannon, and it outperforms Mamba with or without Cannon. You can compare it to, for instance, those two are the Mamba layers. You can compare it, and it also outperforms like Llama. But here, actually, the comparison to Llama to Transformer actually is an illusion. So I'm going to revisit this in result 6. But at least among the linear models, you see like from this table like very strongly that gated linear attention plus Cannon is really performing on par with GDN2. So for such reason, we really call our result 4 that is Cannon lifts the performance of linear attention to a GDN level of the performance. And not only on those benchmarks, but even if you look at the training curves, they become nearly identical. So let me show you. So here are the training curves corresponding to GLA and GDN. So if you look at the dotted ones, those are GLA and GDN. But if you add Cannon layers, so those solid lines correspond to GDN plus Cannon as well as GLA plus Cannon. So if you allow me to like quickly summarize it, it's like without the Cannon layers, then GDN performs better than GLA, but with the Cannon layers, they really like suspiciously like match in the training curves. So the first time I saw this, even the bumpy things are exactly matched. So the first time I saw this, I was also surprised. I even very carefully checked my code to make sure I'm training 2 different models. I verified it already. So the only reason you're seeing this kind of matching bumpy is because I'm using a super aligned kind of experiment control. That is, I made sure all the training data and the data shuffling are exactly identical. So that's why you see the bumps, right? So this is one of the beautiful things about doing such super alignment across the models. So therefore, like you can conclude just by looking at this training curves that maybe using GLA versus using GDN, like once you introduce the Cannon layers, maybe don't matter at all. So let me actually remind you, what is the difference between GLA and GDN? So GLA was the idea of like adding to your memory module, on top of that, some key transpose V, so that's a rank 1 update to your memory module. That's like the idea of linear attention. And in gated delta net, it adds on top of this a forgetting mechanism. So it allows you to selectively like forget in one of these dimensions, the key dimensions in your memory matrix. So of course, this forgetting, is a very smart design, but we're saying that, based on, not only our synthetic experiment of the previous talk, but also on the real life experiment of today's talk in this large scale, we discovered that Cannon really closes the gap that previously attributed to the GDN's smartness. So sometimes the simplest explanation really is the explanation. So maybe this kind of forgetting mechanism is not doing something very smart. It may be just doing something as simple as some horizontal information mix. So in the next result, let's see this picture even bigger. That is, let's see like Cannon's horizontal mixing performance across architectures. So there are so many results. So I tried my best to summarize them, in a table that's as concise as possible. So our main discovery here is that Cannon really delivers the largest marginal gains to models with the weakest horizontal mixing. So let me explain. So if you look at the transformer or the Llama architecture, it has no horizontal information flow. And therefore, like if you add Cannon layers, it performs the largest gain. So this is for 1.3 billion model, 3 billion, and 8 billion. It provides the largest gain. And if you look at perplexity or accuracy, so all of them have such a huge gain. And if you look at GLA, linear attention, it's a naive architecture. And even if it already has a Conv1D version to provide some information flow horizontally, but it's very limited. So therefore, like by adding Cannon layers, you also see this kind of very huge gain in all the cases. If you look at GDN, it's a smarter architecture. Its Conv1D version provides a better horizontal information flow. And as a result, if you continue to add Cannon layers, you see about the gain gets halved. Okay. And if you look at the Mamba, it's sort of the worst. So to my mind, like I think Mamba 2 has maybe a smartest SSM design among all the models, but you see that the Cannon's incremental gain becomes even very limited. Only like some gains in the 3 billion size, but not in the 1 or 8 billion size in our experiment. So therefore, like Cannon-induced gains is really the largest on the Llama and the GLA side, and medium like on the GDN side, and like negligible on the Mamba 2 side. And keep in mind that this comparison is already on top of the Conv1D versions of those linear models. So this is why, so therefore, like this statement is actually a bit conservative in terms of Cannon's gain, because we're talking about just adding the Cannon ACD on top of the Cannon B. So if you compare to their base models without the Conv1D, then the gains will be much, much bigger. But very importantly, that is all of those gains I'm showing you here are truly not observable at academic scale pre-training. So I showed you in the previous video. But here, like if you're willing to spend a lot of money, like 10K or 20K or 50K for each of the runs, not to say that we run it for multiple learning rates and taking the max, so that's much more than this, then those observations will start to show up. So therefore, like if you don't have this amount of money, then I really strongly encourage you to look at our synthetic pre-trained playground. So over there, the gains will be much, much more amplified. So for instance, you're going to see that the GLA plus Conv1D versus GLA plus the Cannon ABCD, then the gains here is very dark here and very bright here. So you see like a huge gain, like the differences in the accuracies are much more than just a few percent. And if you look at, say, Llama versus Llama plus Cannon, like it's also like very huge here. And keep in mind that all of those synthetic experiments can be done just within like 100 million trainable parameters of the model. So that's like, I think, 2 orders of magnitude smaller than this real-life pre-training. But already, like you can see many of those gains, like the gains from the Cannon layers, very cleanly. But here, like you really need to scale up to, very large scale. So the last thing I want to say here is that I want to bring back actually this picture. That is, I showed you that without the Cannon layers, then GDN or maybe Mamba, so I showed you only GDN here, but Mamba as well, they actually all beat linear attention. So this is the same as what people like commonly have observed. But with the Cannon layers, things are, the conclusion really got flipped. That is, GLA becomes identical to GDN, and they're both like much better than Mamba. So here, like you can see that GLA and GDN are much better than Mamba, and much better than Mamba in all the cases. So based on this, I can really like confidently make the conclusion that is most of linear models, at least the ones we tested, like most of GDN and Mamba 2's advantages really come from the horizontal information flow, but not their architecture complexities. In other words, like architecture cleverness helps, but it turns out horizontal mixing does most of the work. So you may have heard me of already, making this strong conclusion in the previous video, but that was using the synthetic playground. But today we're now seeing this, in large-scale real-life pre-training. That is, even in such a big scale, we still see that the architecture cleverness, like behind, say, GDN and Mamba 2, maybe don't really matter. It's actually the horizontal information mix, the Cannon layers, that is actually playing the most important role. So this is why, like I call result 5, that is, Cannon's horizontal mixing really dominates architecture sophistication. So this is the place I want to bring back this picture once again. That is, existence is cheap, but learnability is everything. So you can design your architecture to be arbitrarily complex. But in the end of the day, what does SGD or Atom actually learn could be a really simple function, like maybe I'm representing it by 1 plus 1 equals to b here. So therefore, sometimes the simpler, the better. So you may want to design the architecture to be simple to begin with, like the Cannon layers, in order to get the best performance. So this actually summarizes result 4 and 5. But that's still not the end of the talk. I'm going to show you even more surprising results, 6 and 7. So in result 6, I'm going to tell you that the linear models really fail at in-context retrievals. So I have shown you in result 4 that linear models can even outperform transformers on those like LM evolved benchmarks. So that was this table. I told you that GloB5 plus Cannon is better than transformers. And many linear architecture authors have already discovered similar things. So they use that to claim that their discovered architectures are better than transformers. But in fact, let me tell you that if you look at a different set of benchmarks, this comparison can be totally flipped. So those are the benchmarks on the generative or retrieval tasks. So let me explain. So this is the very careful experiment we did on top of a different set of benchmarks. So those are the generative or retrieval tasks, such as, for instance, trivial QA and so on. So those are the ones that the model is given like the context, say, about the Titanic, and then it's asked about who found the remains of the Titanic. And the model has to, word by word, answer correctly about the name of this person based on the context. So those are the generative or retrieval tasks. And another set of tasks we look at is the Babylon long context reasoning task. So those are the ones that look like the following. So Mary went to the bathroom, like John moved to the hallway, and Mary traveled to the office, and where is Mary? So the model has to do this retrieval to find out like where is the last kind of occurrence of this person Mary and where like she had to do and so on. So this is only the QA1 version of the Babylon task. We tested also the QA2, QA3 until QA5, and we plotted kind of the average accuracy here in this column. So what we discovered here is that if you use linear models, those are linear models, so Mamba or GLA or GDN, versus transformers, then you see a huge difference. So transformers are a lot better. They are, for instance, a lot like brighter in the rows comparing to the linear models. So therefore, like linear models are just not good at such in-context retrieval tasks. So actually, even stronger than this, I'm going to tell you that linear models not only fail here, they fail even at the most trivial kind of cases of in-context retrieval. So this is actually the data set. This is actually a new evaluation benchmark that I'm going to introduce. I told you already very briefly in the previous video, but today let me make it very concrete. That is, let's talk about the following kind of 6 sentences, like some random person's name was born in the year of some random random year. And you repeat this for 5 different people and then answer me. Like say one of the person like was born in the year of blah, and you let the model to continue to fill in a number. And if the number is correct, then you give it a score. So this is what we call the birth year retrieval task. Only about 5 facts. And later, we also embed this into a randomly chosen like a Wikipedia passage of length L, of L tokens. And then we try to evaluate those pre-trained models on this birth year retrieval task. And then we discover something very like surprising. So once again, like transformers are much better than the linear models. But this time, we take a closer look. That is, I claim that the linear models actually fail significantly already on short context. That is, if you look at this column, so those correspond to L equals to 0, so I'm not having any distractors. I'm not having any Wikipedia passage. And you see that transformers can achieve like 99.9% accuracy, but linear models, only if you use like an 8 billion size model, you can get maybe 97% accuracy, but otherwise you only sometimes get only 90% accuracy and so on. So therefore, like linear models already significantly fail on short context information retrieval. So those are only 6 sentences, right? How hard could it be? A very, very trivial setting. And they also fail significantly on long context. For instance, if you look at a context length of 4K, Okay, so then the accuracy just drops to about random guess, that's about 20%. So keep in mind that for transformers, we pre-trained everything like for context length like 4K, and that's why like you can see very good accuracies here. But for linear models, we actually give it a little more advantage, if you remember. That is, we're pre-training it for sometimes a longer context length. For instance, 1.3 billion model, we pre-trained it for 16,000 context lengths. But it already fails at 4K, and even like fails already very strongly at 2K of context length. So therefore, like linear models really are no solutions to long context tasks. So this surprised us too. So it may contradict with something you have seen like maybe in other papers that they tell you that linear models are very good at long context retrieval. But that's because they were studying an even simpler case. So they typically study the needle in the hairstyle dataset. In such a dataset, you don't have 5 facts, you only have 1 fact. And also you have a very magic number, like say a 7-digit random number. So in such a case, it becomes much easier for the model to actually recall what is this number, because it's such a special number that it gives the model a very strong signal about, oh, I had better kind of memorize it. But today we're talking about this like birth year retrieval task, which is maybe in some sense like a second most trivial setting in terms of the birth year retrieval. But we already see that the linear models just totally fail on this task. So, and this remains true despite that, we did already heavy pre-training, and despite that long by long, we actually mean just very short. We just mean like 4,000 tokens. And despite that, we are already taking the simplest or maybe the second simplest retrieval task, and still like the linear models really significantly fail on this. So this is why we said linear models fail at in-context retrieval, even at trivial settings. And if you ask me, like, why did this happen? Actually, I tried to explain this in the previous video already, but today I'm going to add more context. That is, in the previous video, I said, I told you the following, that is, using the synthetic playground, we discovered that linear models, like it can be GLA, GDN, and Mamba, they all like learn one-hop reasoning, which is exactly just one-hop information retrieval, too slowly. So like this slowly. But if you compare that to transformers, it not only learns like 1 hop, it even learns like 2 hop and 3 hop and 4 hop like very, very quickly. So therefore, like linear models, we concluded in the previous video that they are inefficient in terms of compressing and retrieving information from the context. So that was what we discovered using the synthetic playground. But today I want to see something more than this. That is in real life, people do SFT using like long context fine tuning, or they also do RL like post training. But this issue of linear models, it cannot be fixed by SFT. It cannot be fixed by RL, because in the synthetic playground, we already use the highest quality of the data, and still like the learning speed is extremely slow. So over there, like we have perfect data of 1 hop and 2 hop and so on. So therefore, like it's not a data issue. So if you do SFT and RL, it's just changing the data distribution, right? So therefore, like even if I give you the highest quality data, you still cannot learn this quick enough. So therefore, it's an architecture issue. So the linear models are just no good at long context tasks, period. Okay, so you may find this surprising, and indeed, like in practice, why do people still use hybrid models, right? I'm going to tell you that hybrid models work, but just not the way the story is usually told. So I'm going to tell you that hybrid models are useful because linear models are good at short context tasks, okay, especially the knowledge tasks. So we discovered in the previous video that linear models are good at knowledge, by which I mean at least 2 kinds of knowledge. One is knowledge capacity. They can store like 40% more knowledge than transformer. But on top of that, they can also perform very well like in knowledge-based reasoning that are called knowledge manipulation. So therefore, like linear models are very good at such short context tasks. But in contrast, like transformers are good at long context, as well as some multi-hop reasoning tasks. So that was actually the secret behind how those, real life, hybrid models work. And I claim that, unless this retrieval issue has been fixed for linear models, then hybrid still remains the only option. Okay, so this basically ends our result 6. That is, we also explained as a byproduct, like how do hybrid models work. So in the final result, result 7, I'm going to show you a very, very powerful negative result. That is, two-hop reasoning does not emerge for all the architectures, even at this like 8 billion / like 1 trillion scale. So let me explain. So the benchmark, the test we are going to challenge the model is what we call the birth year two-hop reasoning. So this time we're going to provide the model with 3 facts plus 3 equivalence links plus 1 question, so 7 sentences. So we begin with, just like before, like some 3 random people name like was born in some random selected years. And then we give like 3 more facts about equivalence links. Like for instance, name 4 was born in the same year as name 3, maybe name 5 as name 1 and 6 as 2. And then we ask, answer me. Name 4 was born in the year of blah, and then we let the model continue to generate a year. Okay, so this is naturally like a two-hop reasoning question because the model has to, do this two-hop jump in order to figure out the final answer is this one. So then, just like before, we bury this into a random Wikipedia passage of length L. So what we discovered, very kind of surprisingly, is that even if L equals to 0, so we are not like embedding it into a Wikipedia passage. So in total, we only have 6 facts and 7 sentences. And already that the accuracy of all of the models we consider at this pre-training scale, they already boil down to roughly like just 30% of random guessing. So the only exception is here. That is, if you use transformer plus cannon layers and do the 8 billion kind of 1 trillion pre-training, this time you get about 42% of the accuracy. But other than that, mostly like you just get 30-something% accuracy. So this is regardless of if you use transformers or linear models like GLA, GDN, or Mamba2, regardless of if you do cannon layers or not, and it's even regardless of which version of the hybrid models you use. So I'm not showing you the performance of the hybrid models. We tested a lot, different kind of versions of the hybrids. It can be the alternating layers, it can be the parallel, it can be like with some hybrid gating. We tried many different variants, but none of them work. Okay, so therefore it's a solid no to this task of two-hop reasoning. And we also tried many different English prompts and formats, and the results are similar. So in the end, we just picked one specific set of the English prompts with also some English startup text to facilitate the model. So our kind of our format of this two-hop task is fully open sourced in our GitHub repo. So you're welcome to test it on your model as well. But basically, like all of those models just fail on this task. So this gives us actually 2 very strong lessons. The very first lesson is that it's uninformative to study architecture design, or maybe even optimizer design in real-life pre-training, even at this scale. Okay, so at this point, scaling harder is not the answer. Because think about it, if the model cannot even do two-hop reasoning, what are you comparing to? Right? If you're comparing 2 architectures pre-trained in this setting, but none of them can do two-hop reasoning, what are you actually comparing? So even if you scale it a little up, maybe you can do like 2-hop, but how about 3-hop, right? So therefore, like what an actual kind of architecture comparison looks like using real-life pre-training may be just very limited. It may just be mostly like comparing their knowledge capacity or maybe some very simple information retrieval, but nothing more than this. So this is actually a good time for me to cite this paper. You see how much I like it for a 3rd time of today. But this time I'm going to talk about this paper in a totally orthogonal dimension. That is, they discovered, as I already said, that modern optimizers speed up really reduced to 10% when you scale up, right? But we are saying that this might even remain true if you scale further up, like 30 times larger. But this might not because you're using a bad optimizer. It might not because, for instance, you're using a better architecture. It might be because in real-life pre-training, you're only testing some easy skills. So in such a regime, because you're only testing maybe some information retrieval or knowledge skills, then maybe the architecture and the optimizer choices do not matter. Okay, so therefore, like if you want to perform a true kind of optimizer or architecture research, you'd better really stop using real-life pre-training. You'd better use really our synthetic pre-training playground. because over there you can start to build like synthetic multi-hop data to allow such kind of reasoning skills to emerge at a much smaller scale. Okay, so that allows you to study architecture differences or maybe optimizer differences more cleanly. So I really encourage you to use this instead, even if like you don't work in architecture research. Say that if you work on optimizers, this is also what you should try. So the second lesson I learned from this is that modern language models really are pre-trained in a way that the reasoning data has been introduced too late. Okay, so our results actually suggest that the multi-hop reasoning supervision must appear much earlier. So let me explain. So in real life, you have pre-training, mid-training, and post-training. And pre-training usually takes very long. So for Quant 3, like it's 36 trillion tokens, for instance. And during the mid-training and post-training procedure, you definitely start to introduce more reasoning data and especially some multi-hop reasoning data. So what we are proposing here is that, in fact, you'd better insert such kind of multi-hop reasoning data at a much earlier stage, for instance, even earlier than 1 trillion token. Okay, so you should not actually wait until the very end to insert such data. So why? Because many of the skills, okay, so we have some prior works to study this like formally, that is, many of those like reasoning or knowledge skills actually must be learned very early. So they cannot be learned via like the later stage of, say, especially SFT stage. So I'm using this quote must be because if you make your mid-training like extremely long and also say double the model size to be precise, then of course every skill is still learnable. But this is not what people typically do. It's not efficient. So therefore, like if you want to have an efficient overall training, you really had better move those, especially the simple kind of multi-hop reasoning data to much earlier, so that the model can start to build those skills of like 2-hop and 3-hop reasoning and so on, along with other skills or like other knowledge skills and so on, so that he can build its capability like starting from a much earlier stage. So I'm not talking about those IMO type of problems. So those should still like continue to be on the post training. But many of those like simpler reasoning data actually needs to be injected to a much earlier stage. So this is what I'm advocating here. That is the future pipelines of those entire training, like pre-training, mid-training, and post-training, might really need to be unified so that some at least simpler versions of the reasoning data needs to be really injected much earlier and more continuously. So this actually concludes results 6 and 7. That is, linear models all fail at 1-hop retrieval, and all models actually fail at 2-hop reasoning. So if you have made it through like all the 3 videos, your attention mechanism, I think, clearly scales, and your effective context length is truly impressive. So thank you for listening and for spending 4 hours of your context budget with me. See you next time. Bye-bye.